Welcome back. After dealing with the theoretical foundations of algorithms in the last videos, in this video we will finally take a look at the first real algorithm, binary search. We will learn how it works, why it is so efficient, and what we can use it for. We have already looked at two simple algorithms. One of them finds the largest element in an array. To do this, it iterates once over all elements in the array and keeps track of the largest value so far. Since we only need constant time per array element, this algorithm has linear time complexity. The second algorithm looks for duplicates, that is, two identical elements in the array. For each array element, it again checks all other elements. If it finds two elements that are equal but not one and the same element, it returns true. In the worst case, meaning when it finds no duplicates, this algorithm has quadratic running time. We've learned already that quadratic running time is not very good. So can we improve the algorithm in any way? Our biggest problem is that the array is in some random order and we need to check all n-squared pairs of array elements. What if we already knew that the two elements we are looking for are right next to each other? That would help a lot, because then we would need to check a lot fewer pairs. What property must the array have so that duplicates are guaranteed to be adjacent elements? Well, what if the array was sorted? Then between two equal values, there cannot be another value, because otherwise the array would no longer be sorted at this position. What do we need to do to find duplicates in an array sorted in ascending order? We look at the first two elements. If they're not the same, the next two, and so on, until we either find two equal values or we reach the end of the array. What running time do we need? In the worst case, we simply walk once from left to right over the whole array. So we only have linear time complexity and not quadratic anymore. Let's return to our first problem. What is the largest element in this array? Because the array is sorted, it must be the rightmost one. This means we can find the maximum of a sorted array immediately, in constant time. So we see that for both algorithms, we can improve the running time by a factor of n if we only allow sorted arrays. In practice, it is often the case that you can solve problems faster if you know that the input has certain properties. So when writing your own algorithms, always ask yourself, what do you know about the input and how can you use this knowledge? Let us now move on to a seemingly trivial but incredibly important problem in computer science. Namely, how can I find a particular value in a set of values? Suppose I have an array of numbers. What do I need to do to check if a particular value, say 5, is part of that array? If I don't know anything about the values in the array, I have no choice but to try out every element. So in the worst case, I have to check each element once to be able to confidently say whether 5 is in the array or not. This means that the running time is linear. But what if the array is sorted? Intuitively, we all know that it is much easier to find an entry in a list when the list is sorted. There's a reason why entries in a dictionary, for example, are sorted alphabetically. The algorithm used to find a value in a sorted array is called binary search. So let's search for the value 5 in this array. 5 could theoretically be at any position. Our goal is to shrink the range in which the number 5 may be located more and more, while having to examine as few values as possible. To do this, we first look at the value in the middle of the array. 15 is greater than 5. Since the array is sorted in ascending order, this allows us to exclude all numbers to the right of 15. And of course, we can also exclude 15 itself. In one fell swoop, we've cut the array in half. We started with an array of length 9, and with just one comparison, we were only left with a subarray of length 4, in which the number 5 might be. And now we search this subarray again using binary search. So once more, we look at the element in the middle. There is no middle element, so let's say that in this case we always look at the element to the left of the midpoint. 3 is less than 5, so only the subarray to the right of 3 remains. Again, there is no middle element, so we look at the element to the left of the midpoint, and 5 is exactly the number we are looking for. So we are done. How can we implement this algorithm? Like this, for example. First, we check if the array or the subarray we are looking at right now contains any elements at all. If not, the value we are looking for cannot be in the array. If the subarray does contain elements, we compute the position of the middle element, rounding down if necessary. Now, there are three possibilities. Either the middle element is our value, then we found it and we're done. Or the middle element is larger than the value we're looking for. Then we have to search all elements to its left. So we call our binary search function again, but pass only the part of the array that is to the left of the middle element. And the last possibility, of course, is that the middle element is smaller than the value we're looking for. Then we search all the elements to its right. Here I've implemented binary search as a recursive function. This means that the function is calling itself. I think that this way you can better understand the idea of the algorithm. Most binary search implementations, however, don't use recursion, which looks like this. Left and right indicate the range in which the value we are looking for might be located. We try to shrink the range until we either find our value or the range is empty. After we've looked at the middle element, we move either the right or the left boundary of the range, depending on whether the value we're looking for is larger or smaller. I think it's clear that binary search is much more efficient than checking every value. If we just iterate over the array from left to right, we can exclude only one array element after each comparison. With binary search, however, we can exclude about half of the remaining elements each time. But how fast is the algorithm exactly? Everything outside the loop just takes a constant amount of time. And also within each iteration, we only need constant time. So the only question is, how many times is this loop executed? Let's assume we need a certain number of iterations to search this array, say 3 in the worst case. What is the maximum number of iterations we would need if the array is twice as large? With only one comparison, we can already exclude at least half of the array and are back to the same length as before. This means, for an array twice as big, we only need one more iteration. If you remember what we talked about in the last video, you might notice this is exactly the behavior of logarithmic time complexity. If the input is twice as large, the running time will only increase by a constant value. If binary search had logarithmic time complexity, this would be very good, because logarithmic running time is much better than linear running time. Let's check that the maximum number of iterations indeed increases only logarithmically. With each iteration, the range to be searched becomes smaller. At the latest, when the range is empty, we will terminate the loop. This means that we are interested in the maximum size of the range after a certain number of iterations. We call the size of the range after I iterations Ri. As long as the range still contains at least one element, a new iteration starts. If the range contains exactly one element, the range will definitely be empty after the next iteration, and we can stop the loop. So the question is, what is the maximum number of iterations we may need until the range size reaches 1? We know that before we start the loop, the range contains n elements, namely the whole array. R0, the range size after 0 iterations, is therefore n. We also know that after one iteration, we can already exclude at least half of the elements. So the range after one iteration is at most half as large as after 0 iterations and thus contains at most n/2 elements. After the second iteration, we can again eliminate half of the elements, so the range contains at most 1/4 of all array elements. After 3 iterations, it is down to 1/8, and so on. 2 is 2 to the power of 1, 4 is 2 to the power of 2, and 8 is 2 to the power of 3. So after I iterations, the range contains at most n/2 to the I elements. The condition for starting another iteration is that the range contains at least one element. This means that n/2 to the I must be at least 1 if the loop goes through more than I iterations. We can multiply this inequality by 2 to the I on both sides, so 2 to the power of the number of iterations is at most as large as the number of elements. To solve the equation for I, we take the binary logarithm on both sides. After all, the binary logarithm is nothing but the inverse of 2 to the power of something. This gives us this inequality. So as long as we've gone through log of n iterations or less, the range might still contain one element, and we start one more iteration. But after this one more iteration, the range will be empty. So the number of iterations is at most the binary logarithm of n plus 1. What is the worst case running time of binary search? Outside the loop, we need constant time. For each iteration, we need constant time. And we've just seen that we take at most log of n plus 1 iterations. So we indeed have logarithmic time complexity in the worst case. So far, we've only found an upper bound for the worst case running time. Theoretically, the worst case might be even better, as we sometimes exclude more than half of the remaining elements. So the question remains, is log of n also the lower bound? Or in other words, is the worst case running time theta of log of n? It turns out that in the worst case, we don't get better than logarithmic running time. I will spare you the details, but it is easy to verify that if the length of the array is a power of 2, and you search for the largest element in the array, that the range size actually decreases exactly by 1/2 in each iteration, which means the worst case running time cannot be better than logarithmic. One cool thing about binary search is that it's easy to extend in order to solve similar problems. So far, our function simply returns whether the value is in the array or not. But what if the function always returns an element from the array, namely the one closest to the value we're looking for? If our value is an element in the array, we simply return it. But what do we do if it's not part of the array? Let's see what happens when we search for a value that is not contained in the array. Suppose we are looking for the value 50 in this array. I represent the two indices left and right as arrows. First, as always, we look at the middle element. 15 is smaller than 50, so we move the left index. Next, we compare 50 with 42. 42 is smaller, so again we move the left index. And 80 is greater than 50, so we move the right index. At this point, the loop terminates, because the range is now empty. We see that the gap between left and right is exactly where 50 would be if it were an array element. So the element closest to 50 must either be 42 or 80, since left and right point exactly to these elements. How do we need to modify our function so it returns the element closest to the value we're looking for? If we find the value in the array, we simply return it. Now let's handle the case where the value is not part of the array. So in line 9, instead of returning false, we now compare our value with the two elements pointed to by right and left, and we return the element with the smaller difference. This code still has a bug. Can you see it? What happens, for example, if our value is smaller than every array element? Then at the end, the gap between left and right comes before the first element. This means the right index then has the value -1, and we cannot access the array element with index -1. There are several ways to solve this problem. Perhaps the simplest one is to check the special case that our value is smaller or larger than all array elements first, before the binary search even starts. Now the function works correctly, always returning the element closest to our value. Since we only added instructions with constant running time at the beginning and the end of the function, the algorithm still has logarithmic time complexity. There are, of course, other ways to extend binary search. For example, what if you not only want to know whether a value is contained in the array, but also at which position it occurs first? So we look for the smallest index where the value occurs. Simply returning the index at the point in the code where we used to return true doesn't work, since the value may also occur further to the left. Suppose we get not one value, but two values a and b as input. And we want to output all array elements that are at least as large as a and at most as large as b. Both problems can be solved very efficiently with a variant of binary search. But the video is already long enough, so why don't you give it a try? Implement efficient algorithms for both problems using binary search, and share your solutions in the comments. Let's recap. We've thought about how to improve the two algorithms for finding the maximum in an array and for finding duplicates. We found that we can often make algorithms faster by exploiting certain properties and constraints of the input. We looked at binary search a simple algorithm that finds a specific value in a sorted array very quickly. We looked at a recursive and an iterative, meaning non-recursive implementation of binary search. We talked about the fact that with each comparison, we basically cut the length of the array in half, and therefore we get logarithmic time complexity. And finally, we looked at how we can extend binary search to solve other related problems. However, there's one question we haven't answered yet. What if the array is not sorted? How can we get it into a sorted form so we can apply binary search? This is the question we want to address in the next videos, where we'll look at different sorting algorithms. I will see you in the next video.